What's up, class? Today we're going to be talking about QuickSort. Just like its name, it's quick, okay? So QuickSort is a more complicated advanced sorting algorithm, but it is also the most commonly adopted sorting algorithms used in actual environments. For example, like the STL sort is also primarily based on QuickSort. So let's take a look at how QuickSort is being done. First of all, it's like a divide and conquer method, and we use it recursively to sort the entire vector or whatever data structure we're trying to sort. It works with a variety of input. It's very versatile, and also that the memory is very optimized because we only need O of 1 additional memory. Of course, because we're trying to sort things recursively, we're trying to call multiple stack frames, so we're gonna have to account for the stack frames also as part of the memory. So let's take a look at the divide and conquer thing. So the first thing is we have to define our base case. So arrays of length 0 and 1 are already sorted, which should be pretty intuitive. Like you can't sort something that is it is already sorted if it's just 0 and 1. And for the induction step is that we guess that an element inside the array is to partition our array. So that would be a value that we'll be partitioning our array based on. So that we will be partitioning our array into the left part and the right part. The right part will be all the elements that is less than or equal to our element elt, and then the left part will be all the elements that is larger than larger than or equal to our element elt. So the ideal case would be the median, but is it worth that we spend time to find the median first? So if this entire vector is random enough, shouldn't it be like if we just choose any random element, it should always serve its purpose, considering the array is also like random enough, right? So we don't have to spend time to like look for the median, because that would just be wasting too much time and also wasting too much. It's pretty expensive as well. All right. So as I mentioned earlier, we form an array, left-hand side and right-hand side, while all the elements in the left-hand side is smaller or equal to elt, and also all the elements in right-hand side is larger than or equal to element. Okay, so let's take a look at, and also we sort these things recursively. Okay, so let's take a look at our simple partitioning. How are we going to partition our code, our vector? So first of all, one important thing that I have to first address is that all the ranges that we're using here for left and right is that we include the left, but we exclude the right? Just like there's most of the data structures we've been dealing with, like vectors, like .end, it's like going past the actual element, the actual last element. So same thing here. So for QuickSort, we pass into a vector or any data structure, and then we have a left and a right two indexes, okay? All right, and then so the first thing is if it's 0 or 1, if the length is 0 or 1, we just return it because that's the base case, it's already sorted. So left plus 1 is larger than or equal to right. You might be asking like, why is it larger than equal? Just because we remember that we do not, the right-hand side is exclusive. So if I plus 1 and equal to right, that means I only have 0 elements, and then the right is not actually part of it. So in that case, it's like 0 elements, so it's part of a base case we just return. All right, and then we define this pivot, which is the previous elt element, and then we call a partition helper function, and then we pass in the vector, the left and right index, and then we just do QuickSort on the left-hand side and also QuickSort on the right-hand side, okay? So let's take a more deeper look into how we do the partition part, okay? So the partition part, we pass in the data structure we're trying to sort, and then we have a left index of this data structure, and then the right index that we're in between, like the chunk of the data structure that we're trying to sort. So pivot, we make it to, so in this case, because we just choose randomly, in this case, we just always choose it to be the last element, okay? So we we minus right. That would be the last element. We choose that as a pivot, okay? So we just keep looping, all right? We just continue looping, and then we start from the very left, okay? We start from the very left, and we keep comparing it to the pivot, and until that we find like a number that is larger than the pivot. So in that case, it should be on the right-hand side, right? So we just keep looping if it's smaller than the pivot. And then when we find one, we go to the next step, the next while loop. We look for an element that is larger or equal to the pivot. That is smaller than the pivot. Okay, so if it's larger than equal, we just keep it there. Note that here is right minus 1 because that we are not considering the because right hand side is always excluded, so we have to do minus 1 to get the actual element that we're trying to access. And we also have the left is smaller than right, this condition, just so that the element doesn't go off the bound and then we cause a sec fault. Alright? So while this is true, we just keep decrementing our right index, and we keep going from left all the way to the middle. And once we find an element on the left hand side that is larger than the pivot, and then an element on the right hand side that is smaller than the pivot, we make sure that left doesn't go past right. Okay, we also have to make sure that so that we don't like swap it twice or something. And then so if that all satisfies, we just swap it. And if we already went past it, we just break out of the loop. Okay, so let's take a look at the we already talked about the left and right. That's just because that we need to keep that so that the right index doesn't go all the way off the loop and cause a sec fault. And also right minus 1 instead of just right is just because in the previous slide when we defined the range, the right hand side is always excluded, just like any other data structure. So we have to do a minus 1 so that it's an actual element that lives inside the data structure. All right. So let's take a look at an example. If we have a vector 2, 9, 3, 4, 7, 5 is unsorted, and then we pick the last element, just like as we did in the previous slide. We pick this as a pivot. So over here, we take a look at 2. We start from the left hand side, and then we go until we find an element that is larger than a pivot. So 2 is smaller, 9 is larger, so we point towards 9. And then we go from here. We do not include the pivot, okay? So we go from 7, 4, which is a smaller number, so we swap these, okay? And then we just keep doing it, and then we will have a partition 2, 4, 3, 9, 7, and 5, okay? So this is going to be on the left-hand side, this is going to be on the right-hand side, and this is a pivot, okay? And then we continue, and then we move the pivot back into the center, right? And then we do this again. We choose 3, and then we choose 9 as our pivot, and then we sort it. So it's going to be 2, 3, 4, 7, 9, and that's how we get our final vector that is sorted using QuickSort. So an analysis of QuickSort is that the cost of partitioning n elements is O of n. The worst case is n squared because the pivot always leaves one side empty, so that means that we're probably picking like the largest number or the smallest number, so that all the numbers just go to the other side of the array. Probably the left hand side or right hand side. The best case we can get and the average case we can get is all n log O n log n. And advantages of QuickSort is that we have an n log n time complexity compared to all the basic sorts which is n squared. And also the efficient memory usage is we just need an additional O of 1 plus the stack frames because we are solving the QuickSort recursively. And also some of the disadvantages is that its worst case is n squared time complexity, and also that it's not stable. What do I mean by stable here is, as we probably have talked in a few lectures before, is that if an element is already in an order, like a specific order, and then when we sort it, if we have the same if we have the same value on the element that is being sorted, it would not change the relative location between these two elements, just like an Excel spreadsheet. Okay, and we can still make it stable, but it will be a lot more complicated. And also the partitioning is fragile and easy to make mistakes. There's a lot of things going on inside the partitioning, so we can easily make mistakes, and these are all just the disadvantages of QuickSort. But overall, it is still a very optimal sorting algorithm, and it is by far actually the fastest sorting algorithm. So that is adopted by what I mentioned before, like the STL, and also like in just a lot of actual coding projects. So that is a quick overview about QuickSort.